more things like hierarchy builders, and figured out that giving some sort of historical perspective on what has been done in computational systems could be a way to trigger discussions, and maybe there are things that we faced earlier in computer algebra system, because one, it's easier, but because it's easier, we went much further away, making huge crazy stuff, and maybe some of the ideas can be pulled one way or the other. There are things there that I've done, but a lot of it is community work. It will be too complicated in 1 hour to say exactly, give credit to who did what exactly. Community work, let's say, and let's say, for short, I was involved. That's abstract. So, we're speaking about general purpose math systems, and a system like this, I should be using. We want to compute with various kinds of numbers, matrices, with polynomial series, symbolic expressions, finite field, elliptic curves, etc. That's just a start. We also want to do combinatorics, and we have a bunch of combinatorial objects, or we may want to do things like this, where we mix symbolic formulas and combinatorial objects and do linear combinations, algebra, this kind of thing like that. You also want to manipulate graphs, and of course you want to do graphs where inside the nodes you have actually combinatorics, and where you could want to have things embedded, geometric objects, etc. So, if we take as example SageMath, and to have an idea of the scale, it's about 1.5 million lines of code, just Sage, plus yesterday it was mentioned that computer algebra systems are often around 10 million if you count Sage, and everything that is below, that's about it. And we have about 1,000 different types of objects, maybe 2,000 methods, functions, and let's say hundreds of contributors. So it can get a bit messy. So the challenges are how to try to structure the library, so this is from a development perspective, how to help the user with having some form of consistency, and if it can be robust, that would be nice. And one key thing is, well, it's hard to write good code. The less code you write, the less chance you have bugs. So try to avoid as much as possible duplication and try to have things that are modular. All right. So to analyze it better, we need to have a look at what a typical computational math library looks like. And basically, usually you have really two parts of very different natures. You have computational kernels. So that's where you will be doing the heavy lifting. Grinding integers, computing with polynomials, and all these things. And it's all about data structures, memory management, doing parallelism, assembly, etc. All right. So I'm not going to worry too much about this part. And then, on top of this, you have a lot of stuff, which is recipes to reduce to this. And one of the quotes of William Stein, which was the founder of SageMath, is that the art of mathematics is to reduce everything to linear algebra. I don't agree. It's to reduce everything to linear algebra and combinatorics. Others may have different perspectives on that. But yeah, when we do a lot of computations, and physicists do this all the time, we reduce everything to linear algebra. Same for mathematics. Oops, sorry. These are the things we know how to do efficiently, and then we try to reduce this. And so then what does it look like? Essentially, it's applying definitions and theorems. And all of these definitions and theorems turns into recipes like this. So we're assuming that we have these objects, and then this can be computed by using some formula, maybe some change of representation, and mapping, blah, blah, blah. All these nice algebraic features they can do. And if we look in Sage, we can see a good part of Sage as being a library of thousands of recipes, like this. And when you do a computation, you pick up a bunch of recipes, you combine them together, and this reduces your problem to heavy lifting down there. All right. The question is how to orchestrate those recipes to have nice features, to have expressiveness, and try to keep some performance. So different systems have developed different methods. So in GAP, you have a GAP selection method. Sage has method selection, which is inspired from axioms with an object-oriented programming. You have coercion model and so on. The main things are method selection, I want to compute this, which recipe should I pick up for this? And doing discovery homomorphism. All right, let's take a very simple example just to see how it goes. I've got an integer, I want to compute m to the power 8. I can do it the stupid way, or I can do it the clever way, right? So this is a recipe here. If m is a matrix instead, I can apply exactly the same recipe. And of course, that's nice because then I've got a much better complexity, right? So I don't want to have to do this for integers and matrices and so on. I want to do it once. Yes?
Sorry, never worked with Sage. So is it really the purpose of Sage that it really computes everything for you? Like you see here that if you just say you have an expression and you want to, well, Sage really evaluates it? Or is it really the purpose that you provide proofs of?
The purpose is to compute. It's a really computational system. Okay. These computations then can inform mathematics. So the reason why I'm doing Sage is because I use it for my research to do a bunch of experiments. Oh, here is this object. What does it look like? It's a painful, large object that I don't want to do on the board. So I ask Sage to do it for me, and it's going to suggest me conjectures. Most of the time, once all this is done, I can forget about the computation and write a theorem independently on this. So most of my results, my research, mathematical research results, don't depend on computations.
Sorry, I also have never worked with this. Is like this isn't a recipe, right? You are just
no, not yet.
Okay.
It's a mathematical recipe at this stage. I can compute m to the power 8 by doing this.
If I could say the obvious, probably many of you heard about Mathematica, MATLAB, etc. So Sage is the, I don't know, most high-profile open source alternative to these commercial products.
Okay, so we don't want to have to do this by hand time. We want to use this recipe. So what's happening? Why did it work in both cases? That's because integers and matrices form a semigroup. I have associativity. So I've got some algebraic realm, in this case, semigroups. So it's a set with some associative binary internal law. And what do I want to do? I want to implement once for all the function that computes, that do binary exponentiation. Yes?
So if you're doing this sort of algebraically on the previous example, you would hope to be able to do that even if you didn't have n, right? You don't want to just do it for 3, you want to do it for m.
Yes,
right?
of course.
So do you need to provide m, or like what happens if you don't? Or like, I mean, ideally you'd be able to say that second line, m8 equals m times n, that those are true without even knowing n.
Okay. Yeah, sorry. So the point is not to prove equality with. The point is to compute m to the power 8.
Okay.
Sorry, yeah. That's, in this setting, this usually works well, but in this setting, people think, oh, this is what we want to compute. Eric is just pointing to the results were the same. So, what I want to do, I want to implement binary exponentiation once for all, and then I want to provide the system with a recipe that says, whenever x is an element of a semigroup, then you can compute x to the power k by using this particular recipe. And once I've given this, I want to note that whenever Sage later needs to compute something on an element that is a semigroup, that it knows that it can use this recipe.
Evidently, it wouldn't be like just iterated power. You would, because then you get only even numbers.
Yes, sure. Well, binary exponentiation. Right. I just put the is the simple case. But yeah, of course, it's for all powers. Okay. But then, of course, sometimes you will want to compute x to the power k, where x is not an element of a semigroup, an element of a group or a finite group. And then there exist better recipes. You can go faster, right? So we want to be able to provide several recipes and one system to choose the best one, depending on what kind of object I'm manipulating. All right. Good. So if we generalize this, what do we want to have? We want in the system to be able to design a hierarchy of realms, semigroups, groups, etc. and specify what are the operations there, provide recipes for this operation, specify exactly for which realm which operation is available, and then whenever I have an object, specify in which realm the object is. So this object is an element of the semigroup, and because of this, I can look at the realm of semigroups and take this operation and apply it to it. So for this to work, in particular, you need to have a selection mechanism. So when I write f of x, I want the system to be able to look at the realm in which x is, look at all the recipes, and choose whichever recipe is the more specific. Okay? So far, so good. So let's have a look at Sage and what kind of realms do we have here. So of course, you have the basic things. You have sets, you have magmas, and I'm not going to speak about the foundations. Sets, right? Let's not speak more about sets. Just sets. Magmas, so you have multiplication, it's associative, it's unital, it's a model, it's a group. So that's a typical thing, kind of thing that we have. So we're modeling basic math concepts like finite sets, groups, fields, graphs, and so on. And this is naturally a hierarchy. So that's a small piece of it. This is a larger piece of it. This is just fields. And everything that you have above fields. Actually, yeah, it's fairly large. So if you look at fields, you will have rings there, semi-rings, and magmas that are both commutative and blah, 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 blah.
Sorry, what would additive, associative, distributive magma and additive magmas be?
It's just you have an addition and you have multiplication.
Ah.
So the additive here says that we're looking at the additive part.
You can combine them, okay.
Yeah. Because, well, you want to have a ring, so you want to have both. And there are silly things in Sage. We do additive and multiplicative completely in parallel and duplicated. We would like to have views like MMT and other systems can provide. We don't have them. So, will you? Yes?
I'm sorry, why is there a distinguishment between additive and multiplicative?
It's purely a notational thing. Whether the operation in Python will go. So, it's a notation thing. Do you write plus or do you write multiplication? And we would want to write the code only one and then an automatic translation of the operations from one symbol to the other. We don't have this mechanism in Sage.
But also, if you have a ring, it is a monoid twice over.
Yes, so we need two notations.
Yes.
So because of rings, we need the two notations. Because we don't have mechanism to rename notations, we have to duplicate.
And is there a difference then, let's say, if you just take the product of two monoids, if one is multiplicative and the other one is additive, is it then definitionally the same as doing it the other way around?
System, well, either you declare it as additive and you implement the additive operation, or you declare it as multiplicative and you write the multiplicative. Well, we have tools, yeah, we can do some of the things, but most of the time you duplicate. Yeah, not happy with it, but that's so far. That's not the part of being the worst of it all. The worst is to come. That's actually the hierarchy. Well, the hierarchy back in 2012, I haven't updated my, no, 2014, I haven't updated them.
That doesn't seem so big, like for everything you have in Sage.
It's not too bad. That's what you need to do mathematics. You need off algebra and things like that. Okay. It will get a bit worse.
I'm going to make a very silly question. That
Yes.
doesn't look planar.
Mathematics doesn't fit in a plane.
Is
Sorry.
it
Is it?
directed?
Yes. Yeah, it's inheritance.
Yeah, well,
Acyclic directed.
Unlike math.
no.
Yeah, well.
The thing is,
It depends what you would.
then
All right. So yeah, it's from a mathematical perspective. Yeah, we have a lot of concepts. It's not that big. If you showed us to computer scientists, people doing usual object-oriented programming, when they see a hierarchy of abstract classes like that, they say, "Hey, you are completely nuts. It's impossible to do something like this that is correct." So what? Well, so what's the difference with usual object-oriented programming? Yeah, and so in particular, I presented this in Python 2015, and people came, hey, no, you are doing things wrong. If you have large hierarchies like this, it means something is wrong in your design. Well,
So if I said that that graph contains every concept in computer science, then...
No. It contains most concepts in algebra and a bit beyond. And concepts in the sense rings, algebraic structures.
And there's also the combinations, right?
Yes. Yeah, that's exactly the point.
I think wouldn't this be very inefficient to do like inheritance and things like this on top of it, like checking every time you're calling something, checking like. I mean, I could imagine this to be very inefficient.
That's a good question.
Just doing the plain object-oriented programming.
It actually works because of caching.
Okay, so they store the hash and.
Well, whatever Python does, but Python is actually able to handle this in a reasonable way. But again, this is for the high-level recipe code. I would want to be using this when computing hardcore extensions, algebraic extensions of finite fields or things like this. It's about piloting the things, high level.
They just implemented the normal object-oriented style, right?
Yeah, or C++ or whatever, or use the plain C and with Fortran, whatever was there and could be reused. And some of them are really down to assembly code in some places, just for hardcore. I mean, when you want to compute with finite fields, you really want. But I'm not doing this. I'm so glad others are doing this, and this is the power of open source that I can rely on other crazy people doing this. I'm doing this crazy stuff. That's enough. So, in general, and so let's speak about outside of mathematics. If it's a hard problem to isolate what are the proper business concepts. So this hierarchy is usually the hierarchy of concepts of business concepts. And isolating the proper concept is hard. And so when it gets that big, it's probably that something went wrong. And so usual recommendation is to avoid large hierarchies. And usually if you get large hierarchies, it's because you didn't properly add a good separation of concerns, and you just have things that are composing themselves. Now, in mathematics, what's happening is that, as was already mentioned, you have actually relatively few fundamental concepts. You have addition, belonging to, cardinality, topology, blah, blah, blah. And then you have a bunch of axioms with associative, compact, etc. And then you have a bunch of constructions. You can take two sets and do the Cartesian, two structures and do Cartesian products, etc. But you have only a few of them. A good thing as well is that these concepts are known by the end users in mathematics. If someone is doing computing with rings, most likely he knows what's there. Whereas when you are developing software for other users, quite often you have to handle much harder concepts than what you manipulate. And actually, so few fundamental concepts. So you would say, oh, then you would just need a small hierarchy. But the thing is that all the richness of mathematics is when you combine this concept. A field is interesting. Why? Because it turns out that if you are simultaneously associative and commutative and blah, 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 if you take all these axioms together, something very special happens and you can do interesting stuff. So you really want to look at these combinations and say something specific about certain combinations. Not all of them, most of them are without any point, but some of them, fields, summarings, Lie algebra, etc. There is something special to it that allows you to provide recipes and do things more efficiently. Yes.
So when you say concepts are known by the end users, like this situation happens exactly the same in MathLab, right? We also have this giant hierarchy of the various algebra classes, and you don't always like a lot of
students don't know about MacMath. I've heard about groups and
like many of these sort of end up existing because they are like the meet or join of two other concepts that are more relative. You know, you end up with some kind of, I don't know, canonically ordered, non-associative semi-ring, and you ask a mathematician what is that, and they'll have difficulty.
So my students won't know about MacMath or this semi-rings or semi-rigs, or all those. These they might not know about, but they know about associativity, they know about class, they know about the basic concepts. And those are certain combinations.
I would argue that's just a cognitive limitation. Like, that's a fact that mathematicians have done this for centuries.
Yes.
Now we are beginning to have the tools to be able to state results in the proper places.
Yeah. So this is really our change in mathematics, is that we don't have to reinvent everything. We can rely on a century of finding what are the right concepts, which is nice. So we can just reuse them and model them in the computer. All right. So yeah, because exactly this, because we have a century of abstract algebra and so on, we have this hierarchy is robust. All right. So of course, this is not a new idea to be using this. There have been pioneers since the 1980s, and I wanted to, I will ask a question later to ask James about what data I should put about axiom. It's been a long project, so I don't know exactly when categories landed in Sage, in axiom, Aldor, Mupad, Robertson. So in all these systems were using a bespoke language. So axiom was using the axiom language, Mupad was using the Mupad language. And we had implemented a selection mechanism which was essentially usual object-oriented programming, and it was based on a hierarchy of abstract classes modeling these mathematical categories. So these are old ideas that have been implemented and used, and back then I switched to Mupad, from Maple to Mupad, precisely because of this. I needed to have some good selection mechanism like object orientation. All right. Where did I? Oh yeah, and so this is code in Mupad. So you say, oh, there exists a thing that are called semigroups, and semigroups inherit from magmas. So semigroups are special cases of magmas. And in a semigroup, you can compute integer powering using blah blah. Yes?
By category here, do you actually mean like a category as in mathematics, or is it more like a class, just as in object-oriented programming? Or?
So technically speaking, it will be behind the scenes. It will be technically implemented by classes, but it's good to have the terminology of categories, and you will see why just after. So the category, and I'm really not doing high category things. It's really, well, speaking about category of groups, and that's because I'm speaking of groups and their elements and morphisms, and these are the objects. It's a good framework to be modeling things, hence the terminology.
Then, if I may...
Sure. That's the point of the talk, is to trigger discussion, so it's perfect.
So if you would say, let's say, the category of graphs,
yep.
Here would, I would expect, let's say, in such a setting, perhaps that you would say that a category is defined as a graph.
Yeah, you have, the problem of category is that this is so much overloaded as a term, and yet it's so abstract that you can do it in many different ways. So here it's really category in the sense I'm thinking of a bunch of algebraic structures and the operations and the morphisms between them, which is a very specific view of categories. This is the one that we're using. All right. Then you had GAP. Again, a system with its bespoke language. And this system is using something a different approach to it. So it's the same idea. You have fundamental concepts, and for each concept, you have a so-called filter, something that tells you, yes, this is a magma, or no, this is not a magma, yes, this is associative or not. And then what you would do, you would implement your code as operation. You would define, there will be an operation. So for example, there will be something like multiplication. And then you are going to say, we will be able to do something like this. For the operation multiplication, if this and this and this and this filter are, say, yes, so if I am magma that is associative, then you can use this method. Okay, so that's the way you declare the recipe. And then there is a method selection that looks at all the filters and choose the right methods based on this information. And again, as you mentioned, it has to be implemented properly so that it's quick. So you have to do some caching and things like that so that you don't spend your time. Oh, am I associative? Yeah, maybe I could do something.
There's no mechanism for ensuring the methods are correct, right? That's up to...
That's up to testing and
Skill.
And so the interesting thing, the very different thing is that the hierarchy is actually not explicitly modeled. It's not in the memory anywhere. So that's how you write it. You define a function and then you say, oh, if I want to compute power for something that's magma associative, then I can use this particular function. All right. Things similar have been done in other systems, like Focal had this notion of species, which I haven't used very precisely. In MathConf, you have canonical structures that have been introduced around 2013. In MMT, you have all these mechanisms about theories. So it's similar ideas that are everywhere. So now we come to Sage in 2008. So Sage was 4 years old at this point. And we were thinking, okay, we need to have something of this nature, of some form. We need some selection mechanism. There were some choices. The first choice that had been done at the beginning of Sage is to use not a bespoke language, not to invent yet another language, but to use something existing. And there was a choice, a lot of different contenders. The last two contenders were Camel and Python, interestingly enough. The choice went to Python.
So sad.
No.
Very good in hindsight.
Both would have nice things. I think and really this needs to be thought for a system like this. It has to be thought not only from a technical perspective, but also from a social perspective. And for the social perspective, Python was a good choice. And also, from an environment when you want to do a lot of prototyping, having the flexibility and being able to change core things in Python was quite nice. But it's a good question. We will need to redo the experiment and come back in 2008 and launch the same project with Camel and see where it would have gone. I wouldn't be able to say. So, was this choice, so since we wanted to do it in Sage, so that's about the time where I joined Sage. And since we wanted to do it in Sage, this was forced. We had to use this language. And we could have done something different, but it was quite natural to try to stick to the selection mechanism of Python, and this is object-oriented programming, the main way you program in Python. It has some specific features that were not there before. It reused some ideas from Magma. It reused some ideas about Magma that you want to have elements and parents. So what do I mean by this? The point is, most of the time you compute with element. You take two elements of fields, you multiply them together. But sometimes you actually want to compute with the algebraic structures themselves. I want to compute the Cartesian product of these two fields. I want to compute the generators of that algebra, things like that. And so you want to have a distinction between elements of a structure and the structure and manipulate them simultaneously.
Are subgroups elements or parents?
Excuse me?
Subgroups, are they elements or parents?
So a subgroup it's an algebraic structure. It's still a parent.
There are just two levels, right? The elements and the structure.
In some sense, three. You have elements, parents, and categories.
Okay.
And of course, it's always, when you have something like this, you always want to have an element that you would want to make a group of group, and then you're... The good thing is, when we do computation, you can cheat a bit and make your way through. But yeah, this has always been a pain. But most of the time it works.
Sorry, are the categories like the idea of Magma? It's just like literally a Python class.
You'll see you have examples that will hopefully clarify this. Things that we added was support for morphisms, support for functorial constructions, things like doing Cartesian product, we'll see a bit more after, and axioms. The main constraints that we had was that a lot of code in Sage is not in Python, but in Python, so compiled Python. So we wanted to have something that would work reasonably well with that. We wanted to have serialization to be able to save objects and recover them, even if the code has changed and messy. We wanted, on one hand, Python is something that really is about fast speed, and usually it doesn't support, well, it's meant to be single inheritance, but at the same time, single inheritance? No. So we had to find a way to combine these, and the main problem was scaling. Yes.
What do you mean by axioms here?
We'll say this preceptor. It would be easier. But it's really axiom in the sense associative.
So Python compiles to C++ or C?
To
Essentially, right?
C. So there is no inheritance in the target language.
No.
Well, we have to find a way from.
With the axioms, I mean, what exactly are you computing with them? Like, what is it?
it will get clear. So let's see what the code looks like in Python. So let's first try to do what the most Pythonic way. So we want to compute with elements, and so we want to compute with elements of a magma, and so an element of a magma must have a method, and it's an abstract method at this level. There must be a multiplication defined, and then if you are in a semigroup, then an element of a semigroup is an element of magma. In addition, you have a powering operation that you get for free.
An object of the class magma element is
An element of a magma.
oh,
So 42
okay.
is an element of a magma.
Oh, sure. You define the. Shouldn't you be defining a class magma with a multiplication?
That would be, if the class was magma, then the elements would be the magmas themselves. So they would be about operations. How do I take the ring of integers and ring and do something about them? So here it's about the elements themselves. And then once you have these abstract classes, you can have a concrete class. So this is my semigroup, which has this particular multiplication, which I define here. And because I've inherited from this, I get the powering for free. Okay. Now, you want to also to do computations on parents, so on the magma themselves. So for example, I've got a class semigroup. So an element of this is a semigroup, so it's also a magma. And it may have methods such as what are the generators of semigroup. And once I've got generators, I can implement a method to construct the K graph, while assuming it's finite. And then I have concrete class. This is my semigroup, and I define what the semigroup generators are, and from there I can inherit the recipe for computing the K graph.
What is the type of semigroup generators?
It returns a list of elements of the group.
Yeah, but those elements implement the magma itself.
So so this is going to return a list of elements, and these elements should belong to this.
So it's more like a representation, let's say, like a representation of group.
Like my question is an element of magma is a class?
No, it's just plain.
Yeah,
42. 42 is
no, an element, not a something that implements the class magma. Is that a class of elements of a magma?
So if I want to implement my own magma, I need to implement two things. I need to say, how do I represent the elements of the magma? What is data structure, etc. And I also need a class for the magma itself. Two classes, one for the elements and one for the... If I only care about computing with elements, then the class for the parent is going to be small.
So you can take that magma element 42 and ask it, like, what is your parent? And it will tell you nats, which is a magma or something.
And if you call semigroup generators, or I don't know, no such thing as whatever, magma generator for whatever the net, it might give you one as an instance or an object which has as a class, the class of elements of that.
I believe that's right.
Okay.
Yes?
So, going back to a question from way back. So, is it here where you really see also this difference between this additive and the multiplicative? If you say, like, you want to have the clause of rings, you can say...
It says, here I've outcoded something, that this is the star sign in Python, the multiplication sign. By saying the name of this method in Python is the name for the multiplication written as multiply.
Maybe my question was maybe, so let's say you want to define the abstract clause of rings. Would you then say clause ring element and then between brackets both like multiplicative and comma additive or something?
Yes, exactly. Okay, I would denote it from both. I am a multiplicative monoid. So this is, when I say magma, this is imprecise. If I want to be fully precise, and I will take this one, this magma here is a class of magmas with notations multiply and 1. And yes?
Isn't it the case that sometimes multiplication is more computationally expensive, right? So you might want different methods for them.
Yes, so in your class here, you can always overload, and if the powering here is stupid, you can have your own powering.
Even though they mathematically have the same structure, but computationally multiplication is just taking a number of matrices, right? So you don't just do the normal multiplication, you use Strassen's algorithm or
Yeah,
something like that.
exactly. So typically here, first, you will always implement the basic operations like multiplication and so on, and that's really tied to your algebraic structure, and most likely you're going to delegate this to some existing software, and maybe some other, or mirroring that has a very specific properties and I can compute this faster, I override. So it's really, you have generic recipes that are always there, and if you don't like them, that's fine.
So are the definitions of the classes themselves, like magma and semigroup and so on, are they like huge because they contain the entirety of Sage, or is there like some way of adding post hoc more methods to these classes so that you can add like an algorithm or whatever it is?
Oh, yes. Classes are objects, so we can always just attribute to it.
You could add, but usually they are not that big because so the class, let's say the class semigroup element will contain exactly the recipe that work for any semigroup, and there are not that many.
Well, I mean, like group, or like group, you know, all the group
Tends to
algorithms,
be-
there's going to be a lot, right?
Yes.
Okay.
Especially, and then finite groups. Ooh.
Yeah.
That's right. And often in this case, actually, it's not going to be in the group class, but for groups, when you really want to have fast computation, it's going to be group with a certain data structure, permutation groups, matrix groups, and these are the ones that will have a lot of hard code.
Like with this approach, how do you add a state constraint? For example, like if you want a billion groups,
So if you want to have a billion group, you will create a new class. So an abelian group is a group, so you have a class abelian group which inherits from group. And you add whatever you want.
And you put in the documentation, don't implement this if it's not commuted.
that's okay.
Yes, okay, you can always extend some nodes.
And you have to duplicate this element and parent thing, so like everything shows up twice.
Frustrating, isn't it?
Yeah.
Good that you're frustrated. Great. So here's what it would. So typically, what it would look like is so for sets you have the class set element, but of course you want to compute with morphism, so you also have set morphism. Then you have magma element, magma morphism, semigroup element, semigroup morphism, and there is some code smell, right? So where is the code smell? Where exactly is the code smell? It's a lot of classes. Fine. But it depends. If you really have something to say about morphism of magmas, anyway, you need somewhere to put the recipe about. So having a class might not be so bad if you actually have code that you want to put in it. At this stage, what's really bad is that here I'm saying that a magma is a set. Here I'm saying that, here I'm saying that, which one? Yes. I'm saying, let's say this one. A semigroup is a magma. Here I'm saying a semigroup element is a magma element. Here I'm saying a semigroup morphism is a magma morphism. You would want to just say this once and deduce it automatically for the rest, right? Okay, so instead of doing this, here is what we're doing in Sage.
Wait, the other thing wasn't Sage.
That's what I wrote first as first prototype, and I was not happy. I threw it away and then started to do this. And then many people complain, oh, but it's not great, usual. Yes, but we have to do it. But a lot of interesting discussion. So what do we do? This category, this thing here, as a first approach, let's say, it's just a placeholder. We're speaking about this realm of semigroups, and I'm putting everything about semigroups in there. So what do I put? I put first semantic information. That's how I tell it that a semigroup is a magma. So I'm saying that the category of semigroups is a subcategory of the category of magmas. And it feels natural in the vocabulary of, in terms of vocabulary, it's natural to state it this way. And so this is a function. This is a function which I can call, which I can compute with, and can possibly reason.
Does category have a default implementation of things that like looks up the parent?
I have a couple of things, yes. But mostly category contains technical stuff.
I mean, for example, I have an abelian group. Hopefully, when you define the category of abelian groups, you don't need to specify the operations. But when you try to multiply two elements, it needs to know how to multiply, so it has to look up the group category.
Yep. So this will be more, we'll need to be able to just check the exact details, but this, what you're speaking about, will be more generic features for parents. You have a class about how you compute with elements and a class about how you do things with parents. And that's where the relation between elements and parent and how you call methods, that's where it's implemented. The category is really about the mathematics. Yes?
My Python isn't that great. What does it mean when you put a class inside a class? Is this like namespaced, or is this you get a copy of it? Or?
It's a namespace. You can already see it as a namespace. Okay, so you could, at first I can say, oh, this is namespace, where I'm putting three classes. And actually you can see these as mixing classes.
Right, but don't you want like a copy of this class for every, like you want a semigroup method and a semigroup parent, and you want the combination, like where are the combinations coming from?
So that's, here, so this class will be about, it will define recipes, methods for parents that are in this category. So this in there, I'm going to put all the methods about the semigroups. In there, I'm going to put the methods about the elements of semigroups, and in there, I'm going to put the methods about morphisms. Okay? And then, from there, when I want to use this, I just define the class for semigroup, and I say, oh, this here will be this, the structure I'm defining here is in the category of semigroups, and then I can define a class for the elements in there. So I'm putting things together, grouping things together.
Are matrices morphisms or elements?
Could be both. But somehow on the category perspective, I'm going to write generic algorithms about them. So I won't be looking at the data structure. I'm not saying something about the data structure. You will have later a class about morphism between two vector spaces and which are implemented in terms of matrices. But that's below. That's on the concrete side. Yes?
Can you say that again? How can you implement the morphism without knowing the data structure?
It's not that I implement, it's I provide either abstract methods, so I just declare there should be a method doing this, or I provide generic code.
Basically, it would be a call to the...
Yeah, everything in there, it's all about abstract classes, generic code that applies independently on the data structure, and when you want to say something about data structure, you put it into a concrete class. Or you call something that's implemented by some C++ library.
So you're kind of defining a superclass, something like that, no?
Yeah.
Intuitively saying.
And you can really see it as, at the bottom you have concrete classes where you say things about data structure and so on, and usually the class hierarchy here is very shallow. And on top of this you have this huge library of generic methods that you can call and get from there.
You mentioned C++ methods. When you gave this example of like Sage is doing, there's like the hard work and then there's the like putting the integration work. Would it be reasonable to say that Python is only doing integration work and then all of the heavy work is just well, not outsourced exactly. But
it will depend on the area, but in many areas, especially when you come to manipulating, doing arithmetic, most of the time it's outsourced. So it's really, the pilot is Python and decide what's the different strategy, and then you have hard workers that do the heavy lifting. Okay, so, and then when you use it, what's going to happen? So here I create, so this is my semigroup, my preferred semigroups. So it could be, I don't know, semigroup of integers and so on. I can ask it, oh, by the way, do you know what is your mathematical structure? And so the semigroup knows that it is a semigroup. And because it is a semigroup, I can ask for its calligraph. And so how did it work? Because automatically, its class here has been built by taking pieces from everywhere. So I've taken all the mixing classes that were relevant for me and I put them together to get the class from. So because of this, I can inherit from all the generic code that was provided.
Stupid question. This is Python.
Yes.
But the prompt says Sage.
Yes. Just customization.
But is Sage a package?
It can be used as a package now.
Okay.
So Sage is a distribution, it's a library, it's a bunch of different things, but it can be used as a, it's a Python.
You could call on command line Sage.
You could do Python and import Sage. Okay.
But I could also call Sage, and that probably just like starts Python, does some customizations. Okay.
There are essentially this is the usual IPython interpreter. You just have tiny customization, like if you write caret, that's going to compute powers rather than having to use star star. Well, it's more, say, a handful of notational, well, syntactical sugars for typing mathematics. Yes?
Or if you use this category graph, you really use it as functions, but is it also, are some of them also really methods in the sense of?
So all of them, or actually these are methods.
So they really change things, your, well, in this case, the semigroup.
Oh, in theory, yeah, they could change S. It's bad practice. That is, most of the time when you compute with Sage, you compute with this mathematical object, the abstract notion, so it doesn't make sense to change 42. 42 is 42. So most of the time when you compute with Sage, you compute with immutable objects. And so you might change data structure for caching purposes. Of course, you also want to compute with matrices. And when you do, I don't know, Gauss elimination, you don't want to copy your matrix all the time. So you do have data structure for the heavy lifting, you do have data structures that are mutable, but most of the time everything is immutable. So you much prefer something that return the calligraph rather than change it. All right. So because I took a bit of time to say, oh, this is semigroup, I could inherit from code, which is nice.
What does MRO stand for?
Oh, MRO, method resolution order. So what this is saying is that if I want to look at the method calligraph, Python is first going to look in your code, and you see, oh, my class was my semigroup, right? Remember? Here it's not my semigroup, it's my semigroup with category. So Python has built a new class, which is my class, plus some twitching to insert the mixins at the proper place.
And you avoid, like, for example, if I see a problem, which is like, this is a tree, is a list, right? And sometimes you declare a class with two inheritances.
So if you look really at the class itself, it's a graph, a cyclic, luckily. Okay. But then you can ask method resolution order, which computes a specific linear ordering.
Yeah, well, the point is that it will look at first one of the parents and then the other, and that shouldn't be a problem because only one of them will implement the method. Hopefully, that's why you have separation between multiplicative and additive. So is that enforced only through like good practice?
So
convention.
Yeah, it's only convention, and the convention is if you implement, so if there are two implementations of the same method, they should have the same semantic. So it should not matter from
in terms of speed.
In terms of correctness, it shouldn't matter which one you call. Okay. And now the convention also is if you care about which one should be called, this is because you have more context. And if you have more context, you're in a subclass with two, and in this subclass, you say, when I compute this, I want this one. Or maybe something like, for a small object, I'm going to call this one, and for a big object, I'm going to call this one. But this has to be explicitly resolved, and should not depend on the order, because when you start to have something that is dense, large, choosing an order that will be meaningful for all possible kind of optimizations and preferred. It's always better to have a ring than a field. Well, that example was stupid. But. Okay. What time is it? Okay, so you make this promise, I'm a semigroup. In exchange of this promise, you get methods. You get all these recipes, which is nice. But you also get tests. Okay. So when you have this object, you can run the test suite on this object, and automatically it will test associativity, test cardinality. It's not proof, it's test. Just take a bunch of elements, try and see if it works. But automatically test associativity, cardinality.
Random elements.
Is that fuzzer? Is it a fuzzer?
Fuzzer?
How does it find the elements?
So for example, test associativity, we could have a look at the code. It will take a bunch of random elements and
how do you take a random element?
As the object give me a random element.
Ah, okay.
Well, it's your responsibility to.
Sure.
Actually, it's not going to be more precise. It's not going to call random elements. It's going to call some elements. So every parent can provide some elements. Typically, that are interesting for testing.
Some elements.
And you have n elements. It is supposed to give an interesting element so that
all the identity, only the identity.
Well, in practice, there are way too many parents in Sage. When you write n element, you get 0, which is completely boring, which is bad. But the documentation says when you implement n element, it should give an object so that the user looks at the element and knows what you're speaking about. That's the theory. Practice in combinatorics, it's not too bad. This is super useful. In my area, I'm spending my time trying to define new semigroups. And this has caused so many mistakes, programming mistakes. So, oh, I thought my rule was associative. Actually, it's not. Oops. Let's do more research. So this is really handy. And if you start to have a ring, you have a lot of tests coming in. And if you know that if all the tests pass, it's not a proof. But I start to be pretty trustful that something seems to be correct. You also inherit documentation. So in practice, how does it work? So we have this hierarchy of categories here, and well, everywhere. And from this hierarchy of categories and all the mixins, I build automatically this hierarchy of abstract classes for elements, and also a hierarchy of classes for the parents, and we have a hierarchy of classes for morphism. So once it's computed, there is duplication in the memory of my computer, but that has been computed from a unique source of truth. Nice. Okay. So to summarize, in Sage we do explicitly model elements, parents, morphisms, and even things like onsets. And you can see it. You can see a category as a bookshelf. It's really, you go into the library and there is this bookshelf about group theory, and you have everything about group theory, like semantic information, what we know about groups, mixins, so code for, mixins for parents, element, morphism, onsets, like code, documentation, tests, and even code that allows, well, we do have some experiments where we automatically build an interface between Sage and Gap, just by little pieces. Multiplication, this is how you do it with interoperability. Addition, this is how you do it with interoperability. And then you inherit everything. The method selection object is based on standard object programming, except that you have this twist that the classes, you don't write themselves, they are constructed dynamically. And then there is, of course, the question is in this gross design, and that's been longly decided. And one of the things, so there are two things that are not that good. The first thing is we're deviating from standard Python, and this brings some additional complexity, like all the tools in Python that rely on exploring the code and drawing a nice diagram for the documentation, well, they fail because they are meant to look at static code, and we're doing this dynamically. And also this means that for programmer, you have a bit more of a learning curve. I wrote this class and I get this one. What happened? Where is the magic behind? And the main thing is about scaling. So let's take an example. I'm taking a finite field, but not the finite field from Sage, the finite field from gap, actually. And I do the Cartesian product between these. So these are the natural numbers, real numbers, approximation of real numbers, and this finite group from gap.
Sorry, Z are the natural numbers?
Well, sorry, integers. Yeah.
That would disqualify the whole thing.
Well, this disqualifies the whole thing. This is not real numbers. This is the approximations of real numbers up to 53 bits of precision. It's not real numbers.
Show me another one.
Well, we have dozens of them, of real numbers in Sage, depending on what you want to have.
The gap, didn't you say that gap was not, it was written in like its own language or something?
Yes.
So
We have an interface that does some,
I see.
and essentially this is all done. You don't exchange the object back and forth. You ask gap, oh, give me the subject, and then you get a handle to the object, and you can compute the handles and do multiplication of handles. And
Is this a Sage thing, this my gap? Or
so you have something like this in Sage native, where all the translations are hard-coded. For a group, here is how we do translation. For a semi-group, here is our translation. And my gap is this experiment where we defactor this so that you only have to explain once how you do the translation for multiplication. Once you've done this, you can ask for an element. Okay? And if it's just, I ask an element of an integer, a real number, and then I can do computation and just does everything for you, which is nice. And then I can ask, oh, by the way, what is the category of this? Well, it's a Cartesian product of a bunch of commutative rings. And because it's a Cartesian product of commutative rings, it is a commutative ring, and it has all these blah, blah, blah.
Shouldn't that be the category of commutative rings?
It has more. Because it's a Cartesian product, these are special commutative rings, so there are things that you can do. You have more, like, for example, this feature that you can ask for an element and just delegate to your things is specific to the fact that this commutative ring is built as a Cartesian product of commutative rings.
Isn't that some, I mean...
It's a super category, which is the commutative.
I know, it's just that, like, morally the point of Cartesian products is that they allow you to delegate, like, they are an independent product.
Yep.
And then I would imagine that the Cartesian product operation could give you an element of the category of commutative rings, which has its implementation, it just delegates, like, without needing a whole category of.
Well, you want a category because, so if you're a Cartesian product, you will explain how you do addition by delegating. You will explain how you do multiplication by delegating. And you will explain how you compute one by delegating.
Couldn't that be an implementation at the level of the concrete thing?
You could do this, but then this concrete thing, we need to know how you do this delegation for each and every possible structures. It will be in one place. You say how you do addition, how you do multiplication, and how you do Hopf algebra, and how you do all in bits. And so by doing this, you can actually split. And so in the category of groups, I explain how I do the specific things about groups. So I can, again, avoid having something monolithic.
So if you asked on just Z, if you just said Z.category, it would say category of integers or something?
It would say it's an Euclidean ring, and I would need to check a bunch.
Well, like a commutative ring would be one of them.
Actually, yes. Let's just try.
Do we have coding?
Do I have the running Sage?
New mail.
What?
Do I have a Sage running on this machine? No. Did I break Sage? I must have broken Sage. I don't have Sage.
The perils of live programming.
Never mind. This is saying something that I'm not using Sage much these days. I have many Sage on my computer, all of them probably broken. Well, let's try later. All right, so at the end of the day, what you can do, all the different things that you get from this guy comes from 44 different categories. So I've been really picking up stuff from many different places. So let's see what it looks like. So this is the category for groups. This is the category for finite groups. So here groups, and then you have these repetition finite groups, finite monoid, finite semi-group, finite sets. Not all of them have no code about finite inverse unital. So among all possible categories, actually, and I'm going to be low on battery, but this may work. In practice, I've only implemented 11 out of the 14 categories, and I've given the explicit inheritance only for 9 of them, and all of these gray things have been deduced automatically. So a bit small game. If I look at the category of finitely generated finite commutative groups, which is slightly bigger, actually only 17 out of the 54 categories have been explicitly implemented, because there is no interesting code to be put elsewhere, and I only had to give the inheritance for 16 out of 32 of them. Let's go further. Fields. In principle, if you would have done the full graph, only a small piece. If you had done the full graph, you would have potentially 2 to the power 13 combination. So not all of them are done, only 71. And the explicit inheritance has been only given for about half of them. And if we look at all of Sage, in principle, you could build from Sage 2 to the power 50 different categories by combination, and only 265 are built, and you have only 70 explicit inheritance that's only given from one of them, so it's not too bad. Yeah, it's going to be time. What time did I start?